is Andreas Schachner. Could you please share your screen?
Yes.
And he's going to tell us about the large-scale structure of alpha prime effects in string theory. Curious about large-scale structure.
Okay, thank you very much, Gary, for the kind introduction, and thanks everyone for staying around for my talk. So as Gary said, my talk concerns alpha prime effects in string theory. And I use the term large-scale structure because I will be interested in understanding the underlying structure of alpha prime corrections from a variety of different angles, although I should say that I won't talk about the large-scale structure in the cosmological sense. So this talk is based on ongoing work in collaboration with James Liu, Ruben Minasium, and Raffaele Savelli. And we are interested in understanding the systematics of high derivative operators that appear in the type to be 10-dimensional effective action. So I assume that most of you are familiar with type to be supergravity, but nonetheless, let me at least introduce a bit of notation. So as you know, massless fields in type to be supergravity arise from little group representations of SO8, where we distinguish the NS&S and Ramond-Ramond sector. And in type 2b, we can define a very convenient basis of fields in terms of the axodilaton, tau, its gradient, and okay, now I lost connection. Sorry about that. And the complex free form. So with these fields, we can write down the tree level action in this way, which ensures several symmetries. Of course, it's invariant under supersymmetry transformation, but it's also invariant under global SL2R transformations, as well as under a local U1, where P and G are charged under the U1, while the metric and the phi form are uncharged. The alpha prime expansion of the type 2b supergravity action reads schematically, where I suppress the second expansion in powers of GS. So here you notice that there are no alpha prime to the 1 and alpha prime square correction to any order in GS, which is due to the large amount of supersymmetry in 10 dimensions. And in fact, the first non-trivial order starts at order alpha prime cubed, which corresponds to 8 derivative operators in the effective action. So these can be schematically summarized in this way in the bosonic sector, where all terms highlighted in blue are known to all string loop orders. For example, the term R to the 4 has been studied very well in the literature, whereas other terms, those highlighted in red, these remain to large extent unfixed. It turns out that at the level of 4-point amplitudes, we actually know quite a lot about the effective action. So this effective action has been derived in reference 1 by Polycastro and Simpis using the pure spinor formalism of Berkowitz, and reads in Einstein frame like this. Now, I don't expect you to remember all of the details for this talk, but what is important here is that, first of all, there are 2 types of tensors that appear here, namely T8, defined in this way, and epsilon as the generalized Levi-Civita symbol, which encode the contractions of the individual tensor structures into Lorentz singletons. The second important feature of this expression is that it is multiplied by a single function f0, which is a modular function depending on the axodilaton, which enjoys an expansion at large values of the dilaton, such that the leading order term corresponds to string tree level, the subleading term to string 1 loop, and then there are further exponentially suppressed D instanton corrections. So what is interesting about this observation is that this is a real function. And in fact, although in principle, you can write down terms that carry a net U1 charge of plus or minus 8, there seems to be no U1 violation at the level of 4-point amplitudes in string theory. And in fact, this agrees well with the bound derived in these 2 references 3 and 4 on the U1 charge. So in turn, this implies that at the level of 5-point amplitudes, we do in fact expect to have contributions from U1 violating terms. Indeed, this has been confirmed in the literature that at 5 points, we, for example, find terms of the form g square r cubed, g carrying u1 charge 1, so this term has u1 charge 2. So if you want to write down a consistent effective action, you have to multiply these terms by specific modular forms, where for the purpose of this talk, we will only be interested in these modular forms, which transform covariantly under SL2C, as well as carry a non-trivial U1 charge. Then the effective action can be written in this way, where, for example, now the term F1 times G square R cubed is invariant under both SL2C as well as the U1. So in the remainder of this talk, I will focus specifically on these 5-point structures, namely G square R cubed and its variant G modulo square R cubed and G bar square R cubed. And I will use 3 different approaches to understanding and deriving the contributions to the effective action for these 3 couplings. The first and probably most traditional approach is, of course, through string amplitudes, which nowadays can be computed very systematically. And from the field theory perspective, the amplitudes receive 2 types of contributions. The first corresponds to a 3-point vertex connected via a propagator to a proper 4-point vertex, plus a second contribution, which is a proper 5-point contact term, and the same also at the one-loop level. If you're interested in constructing the effective action, we're of course only interested in the contact terms, which means that we have to subtract off the first piece of both terms. Luckily, this has been already achieved in the literature. So using the results of these references, we can already write down the effective action for these amplitudes. So let me explain what these different terms mean. So here we have R of omega plus. So this is the Riemann tensor derived from a connection with torsion, where the torsion is given by the NSNS 3 form. Then there is another T8 contribution, which only appears at tree level, a contribution involving the generalized Levi-Civita symbol, appearing both at tree and one-loop level. And then there are suspiciously looking terms involving new tensors Q tilde I. These are simply contractions of 3 Riemann tensors with 6 free indices in a basis that was defined in this reference 6. And it's a bit surprising that these terms cannot be nicely repackaged into these more fundamental index structures, epsilon, epsilon, and T8, T8. Later on in the talk, I will argue why this is actually not that surprising at all. It's surprising from the string amplitude perspective, but from other approaches, it's actually quite natural to expect these types of terms. Lastly, I also wanted to highlight that there are CPO type couplings that are both established in type 2A as well as in type 2B. However, for the most part of this talk, I will ignore these types of coupling, but I just wanted to clarify that these couplings are also present in the effective action. Okay, now before I'm going to try to simplify these very long expressions, let me first show you how these can be completed in the Raman sector. So in terms of the complex spaces of fields, we know that the modular forms appear as prefactors coefficients. And if we restrict the left-hand side to the NSNS sector, we get to the right-hand side by using that these modular functions enjoy this expansion at large values of the dilaton, so that since we computed already the right-hand side from the string amplitudes perspective, we can compute these unknown numerical coefficients A0 and A1 directly from our previous results. And this leads to the following 2 actions for the 5-point contact terms in terms of the complex spaces of fields. Now again, these expressions still look a bit one could argue horrible. They're very lengthy, and there are different types of contributions. There are a variety of different coefficients. So for the remainder of this talk, I want to address the following 3 guiding questions. First, how can we understand this result? Can we check this with other dualities and ideas, for example, from superspace methods? Then I also want to explain how the relative coefficients are determined by supersymmetry, and also want to show you how these expressions can be simplified by introducing new index structures. Okay. So to begin with, I have to make a slight detour by discussing so-called 11-dimensional superparticle amplitudes. So this is a simple formalism to computing 11-dimensional M-theory or supergravity amplitudes using a world-line approach parameterized by Schwinger-Proper time. So this approach was introduced by Stroessler in the early 90s, and there's this nice review by Schubert that I highly recommend. So in this formalism, this has been applied to plenty of other supergravity theories and also gauge theories. But for the purpose of this talk, we will be interested in very special amplitudes, namely amplitudes compactified on 2 tori. And a general amplitude can then be written in this way, where we have insertion of vertex operators encoding the M-theory degrees of freedom on the world line of a superparticle. We integrate over the insertion points of the different vertex operator, and then take traces over fermion operators that appear within the vertex operators, and then integrate over the 9-dimensional non-compact momenta of the superparticle and sum over the kk and winding charges along the compact T2 directions. So this expression looks very similar to what we're familiar with from superstring amplitudes, but here we simply have a world line instead of a world sheet. In these references 3, 4, and 5, Michael Green and collaborators argued that upon taking the limit of vanishing torus volume, this gives rise to effective vertices in the type to be effective action. And in fact, it has been argued that these amplitudes in fact encode information about all string loop orders. So this is a very powerful method to extract information about the type to be effective action. I don't want to go in too much detail here, but I want to give you a brief example of what one of these amplitudes might look like. So one can compute the 4-graviton amplitude using the results of this reference 3, which can be written in this particular way. So now we are still in 9 dimensions. The kinematics is encoded through this prefactor k, which can be written as T16 R to the 4. Here T16 is some generalized tensor structure, and R to the 4 is simply 4 powers of the Riemann tensors. I will explain the definition of this T16 later on. Then in the bracket, we have 2 contributions. The first is proportional to the torus volume, and this arises from the 0 winding mode. And in fact, in the decompactification limit of taking the torus volume to infinity, this gives rise to a contribution to the 11-dimensional M-theory action. The second term is a bit more interesting in the sense that it arises from the non-zero winding mode contribution, where we again discover F0, the non-holomorphic Eisenstein series of which we have, which here arises from taking into account the winding state on the T2 explicitly. And furthermore, the volume scaling here is such that upon taking the limit V0 going to 0, this in fact gives rise to a contribution to the type to be effective action. Now, to make a comparison to our previous string theory 5-point amplitudes, we now also compute 5-point amplitudes in the superparticle formalism. So we look for 2 types of amplitudes. One is the U1 neutral amplitude, G modulo square R cubed, where now the index structure is given by some new tensor T18, which I will specify in a second. And again, 2 contribution, 1 proportional to the volume and 1 proportional to 1 over square root V0. The second amplitude involves a U1 violating combination, where only the index structure T18 appears, and there is no 0 winding mode contribution. And this, in fact, must be the case because the U1 is not defined in M-theory. So upon taking the decompactification limit of the torus volume going to infinity, we expect such a term not to contribute to the M-theory action. However, both of these terms do contribute. Upon taking the limit of vanishing torus volume, from which we derive the following contribution to the type 2B effective action, namely this contribution here, where I want to stress that now these modular functions or modular forms are actually derived from first principles. So we didn't insert these modular functions by hand to preserve SO to C. These arise naturally in these types of amplitudes. And furthermore, the kinematics is now nicely repackaged into some fundamental higher dimensional index structures. Okay, so this is a nice result, but now we have to match this result to our string amplitudes. And this is actually a bit more involved. We have to compute these index structures explicitly, which is a quite cumbersome calculation. But luckily, this can be done by using the results available in the literature. And one indeed finds that, so the left-hand side is what we computed from the superstring amplitudes. And it turns out that we can simplify these expressions using these high-dimensional tensor structures, where, for example, for R to the 4, we find indeed that this T8 minus epsilon epsilon contribution can be written as T16. For the U1 neutral combination, G modulo square R cubed, we find that there is one T18 tensor plus some epsilon epsilon contribution. And very interestingly, in the U1 violating sector, we find that all of these terms can be nicely repackaged into this index structure T18. So this is a very elegant simplification of the original starting point, where now all of these modular functions have been derived from first principles. So let me make a few comments at this point. First, you notice that these previously free QI terms that appeared in the action are now absent. So this is a hint that these higher dimensional index structure are in fact a more appropriate representation of the string kinematics, although they seem a bit unnatural from the string amplitude perspective. Secondly, in the literature, it has already been established that the kinematics in the NS and S sector for H square R cubed at one loop does not match this tensor structure T18. We showed that this is due to a single contribution in the U1 preserving sector, namely epsilon epsilon G modulo square R cubed, which comes from an odd-odd sector amplitude in the covariant RNS formalism, where here odd refers to the odd spin structure on the well sheet. So two of my collaborators argue that that might even be true for higher point and other amplitudes. And there is in fact evidence for these types of terms. However, there's no full proof yet, and would be interesting to understand the terms that deviate from these more natural higher dimensional index structures. And thirdly, and this might be a bit more orthogonal to the rest of this talk, but I at least wanted to mention that in our paper from last year, so in reference 3, we argued that one needs a similar process of integrating out winding states in Calabi-Yau fourfold compactifications of M theory in order to discover alpha prime odd corrections in F theory, and also to explain the modular behavior of alpha prime effects that were discovered in these two references 4 and 5. Where, for example, the pre-potential in the 4-dimensional n equals to 1 supergravity theory can be written in this way with the corrections derived in these two papers. And here you notice that there's a similar modular behavior appearing here that can only arise upon properly taking into account these additional winding states on the vanishing elliptic vibration. Now, while I motivated the above results by discussing superparticle amplitudes, there's actually a more traditional approach to discovering the presence of these high dimensional index structure by looking at a 10-dimensional superspace approach. So in the remaining 5 minutes, I briefly wanted to talk about the superfield approach to type 2B supergravity. So here we make use of a basic fact, and this has been established already in the 80s, in particular by this paper by Howe and West from 83, that we can construct 10-dimensional higher derivative supergravity actions from a single scalar superfield. So in the in the rest of this talk, I want to show how our previous results fit nicely into this framework. So as usual, when we talk about superfields and superspace, we have to introduce some complex supercharges and introduce a scalar superfield phi, which satisfies two conditions. So it's holomorphic and satisfies this quartic equation, which implies that the superfield enjoys an expansion in power of theta that terminates at order theta to the 8. And all of the components fields satisfy the linearized field equations and the Bianchi identities. In terms of the components at the linearized level, the superfield can be written in this way, where the leading order term corresponds to the axodilaton. At order theta square, we have the 3 form, and at order theta 4, we have the Riemann tensor, and then all sorts of higher order terms. Here I suppressed the contraction of indices with the 10D gamma matrices. So for example, the term theta squared G3 corresponds to this combination, whereas theta to the 4 times the Riemann tensor corresponds to this combination. So what is interesting about the superfield approach is that now we can construct the effective action by integrating over superspace some function h of phi. Then upon expanding this function h of phi in powers of theta and integrating out the supercharge of theta, we find all possible maximally one violating terms. So by integrating out theta, we find this action where I suppressed the precise kinematics, which arises from performing this integral. So for example, for r to the 4, we find that there is a contribution T16 r to the 4. And for g square cubed, we find that the contribution is T18 g square r cubed. And this is precisely what we previously discovered from the superstring and superparticle amplitudes, which leads us to conclude that in fact, the linearized superfield is in agreement with our expectations from superstring and superparticle amplitudes. And secondly, one of course expects that there need also be some nonlinear modifications for our superfield in order to explain the U1 neutral contribution. So that this action above here only explains the first term, T16 r to the 4, as well as T18 g square r cubed, but doesn't say anything about these non-maximally U1 violating terms. So for these, we have to introduce some nonlinear modifications of the superfield.
You have about 3 minutes.
Okay, thanks. But before I get to that, let me mention that it turns out that that using the superspace methods, it's actually possible to write down the full effective action for all maximally U1 violating contact terms involving the 3 form and the Riemann tensor. And in fact, the full action at the maximally U1 violating sector is given by this expression here, where the coefficients are determined by some constraint on the modular function, which is motivated by supersymmetry. So these coefficients CW are determined by this equation here, where the DW corresponds to some covariant derivative acting on our modular forms. And we confirm this result in 3 different ways, namely through the linearized superspace methods, superparticle amplitudes, as well as superstring amplitudes, using the results of these 3 references. So in the last minute or so, I just wanted to mention that nonlinear extensions of the superfield have been discussed in the literature in a 5 background, which has been successfully applied to multi-D3 brane solutions, as well as black holes in ADS5 × S5 geometries. And what do I mean with nonlinear extensions? So for example, for our superfield phi, the term theta to the 4, which at the linear level involved the Riemann tensor and nabla F5, at a nonlinear level can also receive contribution from F5 square, G modulo square, and P modulo square, which allows us to define a new tensor, curly R, which carries 6 indices. So a contribution to the effective action is represented by this superspace integral. So this is very nice because one single combination, so one single expression encodes a full set of additional higher derivative couplings, among others T18 G modulo square R cubed. So this is a very nice observation. And in the end, we would like to obtain an expression that looks like that reproduces our previous result from superstring amplitudes. However, this is still work in progress. And once we achieved to define such a curly R, our final result can be simplified using this previous identity for the covariant derivative of these modular functions, such that there are no unfixed coefficients left. And we obtain a very simple result for our effective action. Now let me conclude. I hope I convinced you that by combining these three different ideas, superstring amplitudes, superparticle amplitudes, and superfield methods, one can establish a systematic framework to efficiently extracting effective action from superstring theory. And we hope to continue this line of research by also looking at dilaton couplings in particular, which so far remain largely unexplored at the level at least of the effective action. And we can also, of course, test these terms in reduction to 4 dimensions by, for example, computing the flux scalar potential directly, or also compute the kinetic terms of B2 and C2 axioms in 4 dimensions. And then also it's interesting to explore further this nonlinear extension of the superfield formalism that I introduced before, involving the 3-form and the axodilaton. So that's all I have to say. So thank you very much.
Thank you, Andreas, for a great talk. Any questions? While we are waiting, maybe I ask a quick one. So you went over that pretty fast. So how does the superparticle amplitude know about modular properties?
I'm trying to. Can you say again? Why?
Yeah. So how does the super amplitude know about modular properties?
The superparticle amplitude.
Yeah. So you said you can derive the modular forms from this approach, but from other approaches, you usually use a lot of additional things.
Well,
like
no, I mean that. Sorry. So they also, of course, arise in superstring amplitudes as well. The point that I wanted to make here that here you compute one single amplitude.
Yeah.
You computed one single amplitude. You find a full modular function F0, right, which includes string 3 level and string 1 loop, as well as the non-perturbative d-instanton contribution. In proper superstring amplitudes, you would need to compute first the string 3 level amplitude, the string 1 loop amplitude, then put it together, and then it becomes also, of course, tricky to also include these non-perturbative states. So from that perspective, it's a bit more work to end up with these modular functions, but there are, of course, also ways to obtain the modular functions from there.
Right. Okay.
But maybe Oliver knows a bit more.
Yeah. Well, he's asking a question, so please go ahead, Oliver.
Yeah. Thank you very much for the beautiful talk, Andreas. I really enjoyed the presentation. And I got curious about what specific well-done computation you performed, how you were handling the 5-point correlator of these vertex operators, and how similar the correlator computation is to doing superstrings on the torus.
So for our purposes, what we've done is you can actually ignore the insertion points of these word-line operators, so you don't have any correlators appearing here. Okay. So this becomes, in a sense, a very trivial integral. So this becomes t to the p. But of course, you can go. Let me think. Yes, so from there it becomes quite trivial to evaluate this expression. But I'm curious, what specifically are you on about?
Okay, let's say in the string theory side, you would do certain OPEs among the conformal fields, perhaps some zero-mode saturation in pure spinors, perhaps some spin structure sum in RNS. I was just wondering which subset of these techniques are relevant for you.
That's a good question. I think that this is probably best compared to the Green-Schwarz formalism of the superstring amplitudes. So you simply have some some angular momentum operators that appear here of the SO, in this case, SO9 algebra, over which you take these fermion traces, which results in these index structures T16 here.
Okay. It's mostly zero mode saturation and perhaps
indeed,
a little
zero
bit
mode
of
saturation. Yes,
OPE
yes.
or okay, I see.
Yes. Mm-hmm. But apart from that, I wouldn't say that there is too much difficulty in itself in computing these amplitudes as compared to what you probably expect in string superstring amplitudes, where it's a bit more tricky, I would say. Yeah.
Okay. And maybe a small follow-up. Is there any hope to extend this superparticle analysis to higher orders than alpha prime?
Oh, that's that. I think this has been done by Michael Green at some point, right? So you have to go to higher and higher loop, but then it becomes really tricky to say much about effective action. I haven't looked at it. I think it's possible, but I think there isn't much work in that direction. In fact, that there hasn't been much work in. So what surprised us was that. So this result, for example, this was something that we haven't found in the literature, although it's very elegant and very easy, and it's an agreement with both the linear superfield method. Now we check that it's also an agreement with the superstring amplitude perspective. Mm-hmm. But the methods that we used are very simple. So this has been around since the 90s, but no one has written down the precise kinematics and checked that it actually does match the string kinematics. So this was actually a rather nice result for us. That this captures already the full superstring result. So from one single superparticle amplitude, you get back the full string theory result.
Yeah, indeed. These T18 and T24 tensors look really intriguing. And yeah, we'll take a look at your papers. Thank you so much for the beautiful talk and the helpful answer.
You're welcome. Thank you. Are there any other questions?
I don't see any other hands raised at the moment. So maybe we could conclude the session, but we will leave the Zoom meeting on for a while. So the people who would like to chat with the speakers could